Hello. So the next topic that we will discuss is hybridization. You can copy down the definition for hybridization there, but it's probably not going to make much sense until I explain it a little bit more. The best way to explain hybridization is to use the example down here of the molecule CH4. That's methane. So CH4 is a very common molecule. It's what natural gas is. It's the most simple hydrocarbon. And we know that it has 4 identical carbon-hydrogen bonds that are exactly the same distance apart, that are indistinguishable from each other. When we take the bond energy of them, they're exactly the same. But if I think of, a carbon atom, as we had learned about it a few chapters ago, the orbital diagram would be 1s2, 2s2, 2p2. Look at where it is on the periodic table. That's what we would have predicted its orbital diagram to be. And the problem is that this does not match with the bonding that we observe, because we know that a bond is when one atom donates one electron and the other atom donates another. So you need unpaired electrons in order to make a bond. And this diagram, this orbital diagram of carbon, only has 2 unpaired electrons. So it seems from this that carbon can only make 2 bonds. We know that that is not true. So what we needed to do is change our model, change the model of carbon and carbon's orbitals. And one thought was, well, maybe this is what happens. 1s2, the core electrons stay there, but maybe one of those s electrons moves to a p orbital. And that gives us 4 bonds for carbon. And that makes a lot more sense. But still, this cannot be the way that the bonding occurs. We know that those 4 bonds in carbon and hydrogen and methane are identical. And if one was made with an s orbital and the other 3 were made with p orbitals, there would be differences. We also know that p orbitals are 90 degrees from each other. One's on the x-axis, one's on the y-axis, one's on the z-axis. But that's not the shape of a methane molecule either. So this can't be right as it is. What we have as our current model is something that is called hybrid orbitals. We say that these 4 atomic orbitals, so the orbitals found in atoms, come together and hybridize. What does hybridize mean? It means that they form, hybrid is like mixing together. So the s orbitals and the p orbitals come together and they make 4 identical orbitals. The name of these 4 identical orbitals is, we name them what they're made from. So because they were made from 1s and 3 p orbitals, each of these orbitals is called an sp3 orbital. And now we say that each valence electron in carbon is in an identical sp3 hybrid orbital. You can see it in a picture over here on the right-hand side. So here is the s orbital, the px, the py, and the pz, right? The px, the py, the pz, they would all be those 90 degrees from each other. We know that that's not how the bonding, the shape of methane is. So what must happen is that they come together to form 4 identical sp3 hybrid orbitals. You can see in this color model how the hybrid orbitals are purple because they're made with the blue and the pink s and p orbitals. They kind of look like a mixture of s and p orbitals because they have 2 lobes, but one lobe is much bigger than the other. And they make this shape, this tetrahedral shape. The tetrahedral shape is kind of think of like a pyramid, right? A pyramid that you have, like the pyramids, but a pyramid has 5 sides. And this is really just 4 sides. So these top are in like a, there's 3 triangles coming together and then a triangle making the bottom. So what that means is that these hybrid orbitals are all 109.5 degrees from each other. That is exactly the bonding that we would predict, or that we actually see in methane. So this seems to be the model that best matches our experimental evidence. So all we're saying here is that our ideas of S and P and D and F orbitals are accurate, but only when the atom is by itself. Once it starts to bond with other atoms in a covalent bond, then those plain S and P orbitals start to really not work. This happens in every covalent molecule. Not always does it form sp3 hybrid orbitals. Depending on how many orbitals need to hybridize, need to come together, they can have different names. So this first chart here shows when you have hybrid orbitals that are just called sp. sp hybridization occurs. Think of how there's 2 of them. This occurs in molecules where the Lewis dot structure just has 2, we're going to call them electron domains, where something like BeF2, see how coming off of that central atom, there's only 2 bonds? That means that those 2 bonds need to be identical, so they must be sp hybridized. So the number of electron domains, or the bonds, the number of bonds, is going to equal is going to help you figure out what is the hybridization. sp2 is the next type. sp2, add up the superscripts, right? S1, P2 totals 3. These are for molecules in which there are 3 bonds coming off of the central atom. So boron trifluoride, like this guy right here, right? SO3, SO3 has hybrid not hybrid orbitals, it's resonance. There's resonance there, okay? 3 bonds coming off of the central atom. And then 4, of course, we know is sp3. So this is the first time that we will see this. Not always does it have to be bonds. Water does this. Water doesn't have 4 bonds coming off of the central atom, but water has 4, what we're going to call electron domains. Electron domain means a place, think of domain, domicile, domestic, it means home, a place where the electrons live. So the electrons live in 4 separate places around the central atom. Therefore, the bonding of the central atom is sp3 hybridized. When we have expanded octets, remember we said when we first learned about expanded octets, perhaps d orbitals are involved. And there's a debate as to how much the d orbitals are involved, but there is a theory, and we're going to stick to it this year, that if you have a molecule like phosphorus pentafluoride, where the central atom has 5 bonds coming off of it, then you would take one S, the 3p, and you would take one of the d orbitals. Remember we said expanded octets can only happen when the central atom is in the 3rd energy level or greater, and that is because the 3rd energy level is when we start to have d orbitals. So the hybridization for anything with 5 electron domains is sp3d. And we would take 2 d orbitals and mix them together. So the hybridization, if there are 6 electron domains, is sp3d2, right? ClF5 is this molecule with 5 fluorine and a lone pair. on chlorine. So if you look at that molecule, you will see that, yes, there are 6 electron domains. So we would say the hybridization on the central atom is sp3d2. That's how you're going to need to know this information. You're going to need to be able to draw the Lewis dot structure of a molecule, determine how many electron domains are around the central atom, and relate that to the hybrid orbitals. There's only 5 choices that it could be. SP, SP2, SP3, SP3D, or SP3D2. And this would be if there's 2 electron domains, 3 electron domains, 4 electron domains, 5 electron domains, or 6 electron domains. Okay, so this is just a matching. Remember why this is, because we need to make those shapes, and there's no way that we know how to make those shapes without hybrid orbitals.